This is 5.6. We're in the last section of chapter 5. We're talking about rates of change in rational functions. So rates of change, something we've looked at numerous times. We've looked at average rates of change. We've looked at instantaneous rates of change. Those two terms should be very familiar to you. And now we're looking at those two terms in the context of rational functions. So in functions that look like this. Okay. So the goal is to determine average rates of change and estimate instantaneous rates of change for rational functions. So again, just to review what we've done before, this time we're doing it with rational functions. Okay? Instantaneous rates of change at a point on a revenue function is called a marginal revenue. Okay, so remember, instantaneous rates of change, what is that? We're talking about the slope of the tangent at a specific point or x value, right? Okay, so we're talking about the slope of this tangent that crosses the curve at one point. Okay, so instantaneous rate of change is equal to slope of tangent, right? And the average rate of change is equal to the slope of the secant. Okay, this is 1 point and this is 2 points. Okay, remember, instantaneous rate of change, we can also use what's called the difference quotient. Okay, and if you remember what that is, okay, so there's a quick review. We have the question that says, it is a measure of the estimated additional revenue from selling one more item. Okay, so how much kind of additional revenue we can make at that particular item is our instantaneous rate of change. So the demand for a toothbrush is given by this, where this is our price and X is our number of toothbrushes in thousands. Okay, what is the marginal revenue when 1,500 toothbrushes are sold? When is the marginal revenue the greatest? When is it the least? So the first thing we need to do is to figure out what the revenue formula would be. Okay, so we're down here. So we're determining the marginal revenue, so in other words, the instantaneous rate of change at x equals 1.5. Okay, because this formula here, this equation here, is x is the number of thousands of toothbrushes. So if we're dealing with 1,500 toothbrushes, we're dealing with 1.5. Any questions about that? Okay. The next step is, this is the price. We want to actually deal with the revenue. We want a graph of the revenue down here. So to get that, we multiply the number we're selling times the price. That makes sense, right? To get our revenue, you're going to take the number of toothbrushes you sell and multiply it by the price. So that's why we change the price equation up here to the revenue equation here by multiplying by x. Yes, Ramon?
Why are we finding the instantaneous rate change?
Because it tells us at the beginning the instantaneous rate of change on a revenue function is called the marginal revenue. Okay, it tells us that by definition. The marginal revenue is an instantaneous rate of change on the graph of revenue versus number sold. Okay, and then we're finding it. Why? Because it says determine the marginal revenue. All right. So in other words, it's kind of a roundabout way of asking you what the instantaneous rate of change is at x of 1.5 for this function. Okay. I don't think there was anything too tricky going from here to here. The only difference was knowing that that revenue is number of items sold times price, which I think is pretty clear. Okay, so we can get the average rate of change close to x at 1.5 by using the following table. So there's our centered intervals. I'm not even sure why they show this. This is just a bit of a review, right? We're just doing average rate of change. So you're picking 2 points on either side of the point of interest. But really, we should be going for the instantaneous rate of change, right? So really, for this problem, we could have used the difference quotient. I'm not sure why they don't initially. They end up using it later down here, okay? So what they find, though, by using the centered interval is as they get closer and closer to 1.5 on either side, they get 0.8 816. So of course that's the slope of the revenue. Revenue versus number sold. So that's going to be the average right here. The toothbrush sold for 82 cents.
Interruption. This is very important. Could all the grade 12 university classes please come down at this time for the university application presentation? Also at this time, any grade 12 university-bound students on the spare during period 2 are reminded to attend this presentation.
Okay, so the next thing they do is they show a graph of the function, just so we can visualize it. So there it is in blue. Okay, they've established that by using a graphing calculator. Notice the horizontal asymptote at y equals 5 and the horizontal asymptote at x equals -2. We should be very familiar with this now from the last 2 sections, right? We know how to get horizontal asymptote because the largest degree is 1. It's 5 divided by 1. So our horizontal asymptote is y equals 5. And here x equals -2 is also undefined because we're going to have a number over 0. So we have a vertical asymptote there. Any questions about that graph? Okay, and then they draw tangent lines and you can see where the marginal revenue is the greatest. Okay, it's obviously near the beginning because the slope is the highest. All right. Here they use the difference quotient and graphing technology to analyze the revenue function. I would have done this from the beginning, right? I would have used the difference quotient from the beginning. Again, they're showing an average rate of change. The instantaneous rate of change is determined by this formula here. So this is actually the instantaneous rate of change. And they figure out the same amount, 0.82. Okay, you can see that calculation is actually done up here. So the average rate of change, you get 82 cents per toothbrush. Okay, so that's the amount, not the price, that's the revenue per toothbrush we're making at that particular number of toothbrushes. 1,500 toothbrushes are sold, we get 82 cents per toothbrush. Okay? That's all the same stuff. Example 2. Estimate the slope of the tangent to the graph of this at the point x equals -5. So this is instantaneous rate of change, right? Because we're talking about the tangent, the slope of the tangent. So what do? We use the difference quotient. Here it is, f at a plus h minus f at a all over h. I'm not sure why they keep labeling this as the average rate of change. It should be the instantaneous rate of change. I mean, I guess if you're considering this a second point on the line, that's so close to the first point, so you're not considering that 1 point. But really, this is the formula for instantaneous rate of change. Okay, we get 0.75. So the slope of the tangent at x equals -5 is 0.75. Okay, so this formula, I'm going very quickly, but you know, we're very familiar with this. We've done this now quite a lot. All right. Why can there not be a tangent at x equals -3? Jonathan, why not? Why not x equals -3? What's the problem with that, Jonathan?
Because it comes to 0.
Yeah, the denominator comes to 0, and when the denominator is 0, Joseph? Yeah, it's a vertical asymptote. How are you going to draw a tangent on a curve on a vertical asymptote? You can't. Okay, there's no line there. Okay, if you did, it would be infinity, right? It's going to be extremely high, right? Trying to draw that. Okay. Last example. So we have a snowshoe hare population that's represented by this equation here. Okay, P represents the population size and T is the time in years since the opening of the conservation area. Determine when the hare population will increase most rapidly and estimate the instantaneous rate of change in population at this time. Okay, so they use a graphing calculator solely for this, and you can see the function is here. And I've kind of went through this in detail. There's no real algebraic way without using a graphing calculator to get this. And so the whole point of this example is just to show you, given a graph, what does the instantaneous rate of change mean? It's, of course, what? What is it? Yeah, it's the slope of the tangent. So where is that slope of the tangent the steepest, right? Increase the most rapidly. So it's definitely not going to be here. You know, it might be closer here, but as you can see, there's kind of two twists to this curve. So this is pretty steep here. Okay, and using graphing technology and choosing different points, what they find out is it's at 2.9. The whole point of this example, the takeaway, because again, we're not using graphing calculators, but the takeaway is that the steepest, the biggest increase is where the steepest slope is on the graph. Okay, that's all. Okay, so in summary, and you can see the summary, even going through the summary, it's going to be basically just telling you that it's a review. The methods that were previously used to calculate the average rate of change and estimate the instantaneous rate of change can be used for rational functions. So everything we've learned in the past about average and instantaneous, including the formulas we've learned, can be used for rational functions. You can't determine the average and instantaneous rates of change of a rational function at a point where the graph is discontinuous. So in other words, where it's undefined or vertical asymptote, there is no instantaneous rate of change or slope of a tangent. Yes? Sorry? No. 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 How are you going to draw a line to something that's not there, right? You can't. Okay. The average rate of change of a rational function y at f at x on the interval. This is just review, right? This is average or slope of secant, right? It just takes 2 points and the y2 minus y1, right? That's just the slope of 2 points. And then instantaneous rate of change is represented by this, the difference quotient. Okay, that's why I think it might be a typo in the book where they kept saying average rate of change and using the difference quotient. You can see here it's the instantaneous rate of change. And finally, the instantaneous rate of change at a vertical asymptote is undefined. That's kind of the only new thing that we've added to this lesson. The instantaneous rate of change at points...
Pardon the interruption, teachers. I'm sorry, Mr. Mills. Could you please contact the office, Mr. Mills?
Okay, any questions with this section?